Hello folks, Rashid here, and today we will look into memory mapping or the memory maps, okay, the memory space or whatever you call it. And yeah, in the previous video we looked into this picture, remember? Um, and yeah, we have come out of CPU or RV32i that we have been building. But just to understand how in real world external things communicate with CPU. Okay. And I has explained that, okay, we have flash there, we have SRAM there, we have different controller, interface controller there. In this example, I put only two. And then we also have interrupt controller, and at some books also say that a platform, interrupt controller, PLIC. I call it IC, interrupt controller. Okay. Now, the thing is how these devices communicate with our CPU or and vice versa. And the answer is that this is a system bus. I'm showing as a wide line here, but it basically have address bus, which is 32-bit, and then data bus, and then acknowledgement line, and of course it has some address decoders inside built as well. This is also something we will look into during microarchitecture in more detail. There is no point in giving you theory after theory and a theory. I think it makes sense when we actually creating a hardware. That's where you understand better. But what I want to teach you today is the portion of your address space. Actually, I should call address mapping or address space. Yeah, that's a good word. Where is it? Address space. So if you look at, we have 32-bit address bus. Remember the CPU bus, address data bus. And 32 bits, this is hexadecimal. I took this picture from the book Sarah and David's Computer Architecture RISC-V edition, which has been our reference book in this course. So you see that this is hexadecimal. So each number is 4-bit. Can be from 0 to 15, or I should say 0 to F. Okay, so if again I covered over the addressing and in the computer architecture first part, the RISC-V architecture first part I should say. So 32-bit, and these are 32 bits. Okay, each one is 4, so we have about 8 of these. So your lowest address is all zeros, and your highest address, the maximum address, is all Fs. Correct? Then you also remember that our memory is byte addressable. So we have a unique address for each byte. And our architecture that we have studied is called Little Endian as well, because our byte 0 is here, byte 1 here, byte 2 here, and byte 3. First, second, third, fourth. 4 bytes, 32-bit. So each location in the memory, our data bus is 32 bits, so we can afford to have 32 bits maximum long. But the bit address is 0 is here, then 1 here, 2 here, 3 here, and the next one comes is 4. So that's why you see here our address for this 0-bit, so 0-bit on this location is C, and then D, then E, and F. That's why you put C here, because that's the address of the byte 0. These are all addresses of byte 0 on each location. Understood? So that explains why it didn't go to all Fs. Okay, then this is our address space. This doesn't mean that our SRAM is this. By the way, this all addresses, if you convert into bytes, it becomes about 4 gig. So maximum number of addresses that we can have a look, or data we can have is a 4 gigs. But it's not all the memory. I mean, I think this is the point I want to clarify to you, if it's not clear, that these addresses doesn't mean this is all SRAM. We can make it all SRAM, but it's not. Because the the mechanism of communication between CPU and other devices and all these other devices is that when it wants to access the flash, I mean, from certain to certain address. And by the way, RISC-V spec doesn't drive or doesn't guide you to use what addresses for flash, what addresses for SRAM or the devices. You can do that on your own. That's your freedom. Okay, so let's say we need, I mean, a small, I don't know how much is it, 256 bytes, but let's say we want to allocate some addresses for flash, because when we start our PCB, our system, right, this information was already lost when it was powered down. This always contains data, so we want to put our code, initial code here. So that initial code is going to do what? What it's going to do is going to initialize some of these registers. I mean, some of them we already know, but then it will put some, this is where your code, the actual program, let's not complicate it. Okay, this is where your actual program sits. Whatever program you have created in a higher level language or assembly language that is for CPU, maybe it waits, it's as I said, the CPU that I'm building is very simple. And all the application that I'm taking right now is it's used in industrial automation to turn off fan, to automate switches, to automate any other machine that you have in the factory. That's where this is used. Okay, and it is super low power and it is super cheap as well. Okay, so bottom line is, let's not go too much into details right now. Just higher level, the picture I want you to imagine is that you have some code here, some also special code that is initialized at the booting, and what the initializing, all the register initialization or the startup work that it does. And then it also has a code that actually you want to run on this CPU or microcontroller. It is a kind of microcontroller. Okay, so that is there, and the location we assign is the address from here to here, or actually this to flash all the way here. Before this, the SRAM starts here. So before this until this, whenever we put that address, that means we are reading a location of flash. The address decoder here or the scheme here will enable that it selects this device and it tells that this address is for you, and this location then we are reading and bringing data back. So whenever that address from here to here comes, it means this system bus will know that it is for flash. So we will be communicating flash. So we turn on our computer, all right, and it started reading data from here, and it started the program and all the doing. So all this text is the program. Now this can be your actual program. Remember all the instructions we have been talking about in the previous part. All these instructions are sitting here, and in the program, in the C program or Python program, you can have some constants, some parameters that you have defined. Those are constant. Based on those, some of the things work in your program, and those are also defined here. Understand? Correct? So far so good. So, and it also has some interrupt handler routines. What happens when an interrupt comes here? What sort of when an external interface signal comes here, and all this mechanism, the interrupts and exception, those are the ones we will talk in the next video. So next video will be on interrupt, and the video after will be on exception. So in order to handle those cases, we need to also write a special kit. You as a user of this microcontroller CPU, you need to write a special program, and that is stored also in flash here. All right, so these things are stored here in this section. So understood this flash part? Now the thing is, once you have a program, you have seen that you have some global variables which are used across different functions. They're not just visible. Normally, remember, when you are within a function, you use a stack. But there are some global variables. The stack will be cleared when you are out of a function. but you need some of these variables which from function to function are visible. So these are the ones you need to store here. So we allocate from this address till address. This is for SRAM, and this is where we will store some of the global. I mean, these can be big as well. Don't think these are 2 3. If there are 2 3 global values, fine, great. We can maybe readjust their space, but could be a long array, right? And after that, in SRAM, there's another thing kept, stack. Remember, when we go into the function, sometimes we need to store some variables, or we need to, this is the temporary data that grows downwards. And the stack starting point start with this register. This was one of those general purpose register, one of those 32 registers here that points to this, and all that we discussed previously in the computer RISC-V architecture class. Now I forgot to mention that GP is also another special purpose, general purpose, but still a special purpose register. Register that points to the middle of this global. So if your space is from here to here, figure out what is the middle point, and that's where it's stored. So with this register GP, it can, things can go up and down. So you can imagine that it has a, this is X as a base, and then we have a 12-bit offset to access anything above and below. Clear? Global part clear, stack clear. We start here, we go down as we start removing from it, and we go back here. This thing we didn't cover heap. So this is more of a people who use C language, that malloc, or I don't know if that's the right pronunciation. Basically, you allocate dynamically during the program, you allocate certain memory for certain variables. So this is where that heap is used. Heap, whatever the bottom address is, where the after global data. So our whole configuration knows that after global data, heap will start, and the top address is stack. There is no register that holds this value. Basically, it's taken from the maximum limit and the next four, the next address after that. So dynamic allocation or deallocation and stack is used. So this address, whenever one of these address comes, this bus knows that is for SRAM. Got it? All right, let's go the next level, the top part. And by the way, you can readjust this address. This is up to you. You can maybe put this one down, but this is typically what's being used. So now the CPU need to talk to GPIO, and you're probably thinking why, but whenever a signal outside, I should draw here. Okay, think of that, there's an outside. Whenever outside comes here, let's say a signal comes low to high, and that is what we are detecting. So there's a register here that gets 1 whenever there is a low to high transition. So there could be other registers here. This is like a simple control. This piece, this hardware, this is the hardware actually. We will implement this in system Verilog, or we will take a already finished hardware. We might not have time to design all the controllers, but we will take some open source code. So what we will do is, this guy will have some register that allows CPU to read, means it's ready, or when you want to send something out, right, from here, let's say based on the input you are done, or you are input, you figure out there is a signal went high and you need to process it, and it's a temperature sensor. When temperature reaches a certain point, this need to turn on a fan or AC, so this does it through this. If this interface to do something, there are also register that CPU can write and then output a controller based on once it's written, it will generate some output. So this controller function is to kind of manage this communication between external interrupt controller and the CPU system bus. Correct? And those registers will have an address. Again, this is what exactly means GPIO and UART. This is called a memory mapped. Your GPIO registers or your GPIO is memory mapped. Means its location, its registers have an address. So they will be assigned that addresses based on this hardware, and whenever CPU wants to communicate with them, it will put that address, and that address we have already in our system will know that it's from here. We will put for GPU from here to here, from UART from here to here, and also we will have, I think, the interrupt. We also need to access the interrupt controller register. Maybe we can have something here or here. I don't remember. I don't know. We will all these details. So let's not make our life super complicated. What I want to give you right now, you understand the concept, and the exact details we will do later on when we actually implement them or reuse an implemented version. That's where we can look into details of that. Okay. So the core message from this video is all the devices, including SRAM, this is our master. This guy is our master here. These are all the slave devices. This initiates the communication. These external interfaces can also initiate a communication, but that is the interrupt, and that we will talk in the next. But all these are the devices. They are accessed through a particular address, and whatever address is used for those is called GPI is mapped to that address. Okay, hopefully this is clear. Simple concept, but people struggle to understand, and people struggle to even teach. Okay, I'm not sure if I did a good job, but hopefully you understand the concept now. If not, please let me know. I will try to explain in a different way. All right, guys, thank you so much for watching. Next video will be on interrupt, which is here. All right, see you.